Every part of my body hurts. All of my joints and all my muscles are protesting the crushing pressure of gravity. I'm also nauseated, although I haven't thrown up. A crack of light wakes me. Is it morning? No, it's just Emiko coming to bed. I've only slept a couple of hours, but I feel delirious. It's a struggle to come to consciousness, enough to even move to tell her how awful I feel. I'm seriously nauseated now, feverish. My pain has gotten worse. This isn't how I felt after my last mission. This is much, much worse. I struggle to get up, find the edge of the bed. Feet down, sit up, stand up. At every stage I feel like I'm fighting through quicksand. When I'm finally vertical, the pain in my legs is awful. And on top of that pain, I feel a sensation that's even more alarming. It feels as though all the blood in my body is rushing to my legs, like the sensation of blood rushing to your head when you do a handstand, but in reverse. I can feel the tissue in my legs swelling. I shuffle my way to the bathroom. I make it to the bathroom, flip on the light, look down at my legs. They are swollen and alien stumps, not legs at all. I say, Emiko, come look at this. She kneels down and squeezes one ankle. It squishes like a water balloon. She looks up at me with worried eyes. I can't even feel your ankle bones, she says. My skin is burning too, I tell her. Emiko frantically examines me. I have a strange rash all over my back, the backs of my legs, the back of my head and neck, everywhere I was in contact with the bed. I wonder whether my friend Misha back in Moscow is suffering from the same swollen legs and painful rashes. I suspect so. Our space agencies won't be able to push out further into space to a destination like Mars until we can learn more about how to strengthen the weakest links in the chain that makes spaceflight possible, the human body and mind.
To colonize the moon, you don't just need to get things to the moon, you need to get them on the moon. The budget allocated to develop and build 12 lunar landers back in the Apollo days was $18 billion 2016 dollars, or $1.5 billion per lander. Once again, the lunar landers are no longer in service, so we're including the R&D costs in our calculations. We need 2 landers to bring our 4 astronauts to the moon, and these have to be able to return, so they need to land with both launch systems and fuel. So that's 1.5 billion per lander, plus 4 billion per Saturn V launch, so 11 billion total to carry our astronauts to the moon and back. During the Apollo days, NASA also developed a module called the LM truck, which was designed to deliver payloads to the surface of the moon without a crew. Not only could these land with 11,000 pounds of cargo, but a Saturn V rocket could launch with 2 of them. Using the truck, we can bring our per pound cost of bringing cargo to the lunar surface down to a reasonable $318,000. How much would it cost to live a year on the moon? I'll just say before giving my answer that these were all estimates and far from perfect. For example, it's likely that if NASA ever actually colonized the moon, it would be decades in the future when commercial space companies are far more developed and the cost of transport would be much less. Elon Musk is anticipated to announce SpaceX's plans to get to Mars, including a massive rocket that will be able to carry as many as 220,000 pounds to Mars for less than any previous rocket, which could make Martian colonization economically feasible. So, after adding everything up, my conservative estimate for 1 year with 4 astronauts on the moon comes out to $36 billion.
last decade, there's been a lot of hype about humans going back to the moon. Japan's space agency JAXA was planning to have a fully functional moon base by 2020, but that plan fell through. NASA declared they'd have one built and fully staffed by 2024, but their plan shifted to an orbiting lunar station rather than a surface one. Clearly, there's a reason these ideas keep getting nixed. Let's start with some lunar basics. It can reach 250 degrees Fahrenheit during the day and drop to negative 380 degrees Fahrenheit at night. The moon has basically no atmosphere protecting it from the constant barrage of harmful UV rays from the sun. These solar rays can do some serious damage to your fragile human bodies, especially during solar storms when the moon's surface can be hit with hundreds of rems of radiation. Gravity is another problem. The moon's gravity is 1/6 that of Earth's. Levels that low drastically weaken your muscles and bones and even changes how your heart and nervous system function. The moon's environment isn't ideal for building either. The moon's surface is covered in a layer of something called lunar regolith, and it's really hard to dig through. Astronauts even had problems with regolith during the short Apollo missions. It built up in their spacesuits and equipment, stiffening joints, freezing switches, and disrupting hydraulics. People have argued that since regolith is partly made of oxygen, we could mine that oxygen to create water, breathable air, and rocket fuel. But in order to do that, the regolith would need to be heated over 1,500 degrees Fahrenheit. And getting machines to the moon that could heat up that regolith, as well as ones to construct buildings and generate energy, would be tricky to say the least.
It has been 50 years, only 50 years, since actually humans set foot on the moon. However, in the intervening 50 years, there have been quite a few key discoveries that have enabled us to even consider returning to the moon with an aim that actually we are going to stay there for much longer than a few days, perhaps weeks, maybe months at a time. In order to enable that, you need to be able to live off the land. About 20 years ago, there was a discovery of water ice on the lunar poles. That was a game changer because up until then, it was considered that the moon was bone dry. The water that is present on the moon as water ice may be directly accessible and usable as liquid water, but there is also water locked inside the lunar minerals. And perhaps the water is going to be the first resource that human beings are going to need, not just for survival, but for actually using the water to produce rocket fuel.
So what we are looking at here is a machine that is called NanoSims, and what this machine does is it bombards the lunar sample with high energy ions, and those high energy ions then actually release the atoms and the ions that are present in the lunar sample. There is no free-flowing liquid water in these samples. Instead, what we are interested in knowing is how much of hydrogen is present in these samples. And most of the time, this hydrogen is going to be present together with oxygen. And if you combine lots of these hydroxyl molecules, you could actually produce water as you know it.
So the experience that a person would have of living on the moon perhaps could be seen as being similar to what astronauts experience when they are on International Space Station for extended periods of time.
It feels as though all the blood in my body is rushing to my legs, like the sensation of blood rushing to your head when you do a handstand, but in reverse. I can feel the tissue in my legs swelling. I shuffle my way to the bathroom. I make it to the bathroom, flip on the light, and look down at my legs. They are swollen and alien stumps, not legs at all.
Orion is different from what we had back in the Apollo days. As you would think, over the last 50 years, we've had a tremendous amount of technology developments. So I would say that Orion is smarter in some ways, thankfully, because we've had so much development in computing technologies and efficiencies of life support systems. The actual volume, while it may seem small to you, it's much bigger than what we had back in the Apollo days. So we wanted to give the crew members a little bit more space so that they could do their work and their operations with a bit more room. Artemis 2 will send up to 4 crew members, kind of similar to Artemis 1, just around the moon and then come back to Earth. So really that's a test flight to evaluate all of our systems with humans on board. In the capsule, we still have to exercise. We don't have a lot of space, so we're looking at new exercise technologies that'll do things like rowing and allow us to just switch up a few of the modalities on the device, and then you can do squats and deadlifts and the kinds of exercises that you want. The human body doesn't like microgravity. We're not designed to be in a microgravity environment, and over time, if you don't do things like eat properly, drink enough water, and exercise, your body is going to start to get lazy. You're going to lose muscle, lose bone, lose cardiovascular endurance, and while that may have some impacts to while you're in space, even more so is when you come home, we want you to be able to walk and interact with your family and get back on the treadmill and start running again. And so we think about the human risks not only during your mission in the hostile environment that is space, the vehicle has to protect you from all of that. We still have our sights set on humans going to Mars. Going back to the moon is a smart way of doing it. We are really learning so much even today with the space station. Now, going back to the moon seems like a smart idea because it's just a little bit further away. It's, rather than a couple of hours to get to the space station, it's going to be 2 to 3 days to get to the moon. Whereas Mars is much, much further away. So the complexity of your systems grows the further away you get from home. And the goal is not only to go to the South Pole in 2024, plant the flag and be like, woohoo, we're done. It's to then learn and evolve those missions so that by around 2028, we'll be able to actually live on the moon for longer and longer durations and do it in a sustainable way. From what we learned from the moon missions, we will then be able to, in parallel, continue to develop our plans and our technologies to send humans to Mars.
I make it to the bathroom, flip on the light, and look down at my legs. They are swollen and alien stumps, not legs at all.
This is Ask NASA, and I'm here to answer your questions.
The two large spherical tanks there were pressurized with dry nitrogen because if the film was in space in a vacuum for an extended period of time, the emulsion would, and the water in the film would evaporate. So we had to keep it pressurized at a very low pressure, like less than 1 pound per square inch.
engineers of the Boeing Company and the National Aeronautics and Space Administration are making final preparations to launch one of a series of lunar orbiters. The satellite's primary mission is to photograph landing areas on the moon for America's astronauts. An Atlas Agena booster will launch the orbiter from Cape Kennedy. When orbital speed and altitude are achieved, the Atlas booster and nose shroud will separate, and the Agena will fire to place itself and the lunar orbiter into a 100-mile-high orbit around the Earth. They must travel to the exact point in space from which Agena can put the lunar orbiter on its path to the moon. When this point is reached, Agena fires again. Soon after burnout, Agena separates, and the 850-pound orbiter will be on its way. Now speeding through space at 25,000 miles per hour, the vehicle will extend its two-way Earth communication antennas. And solar panels will open to capture and convert the sun's energy into electrical power for orbiter's systems. Tiny attitude control jets located on the corners of the heat shield will be fired to position the vehicle to aim its solar panels toward the sun, and aim its tracker for a fix on its navigational star, Canopus. After 15 hours of flight toward the moon, Lunar Orbiter will fire its velocity control rocket to make a mid-course correction. Later in the journey, as the orbiter gets closer to the moon, the velocity control rocket will be fired again to slow the spacecraft. This will serve to trap the spacecraft in an off-center orbit around the moon, where it will circle from 4 to 6 days. By tracking this orbit, scientists on Earth will obtain their first precise information about the effects of the moon's gravitational field on the spacecraft. With this knowledge, they will be able to lower the vehicle's orbit to a close 28 miles for photography of the moon's surface. Control of the spacecraft is accomplished through instructions stored in an onboard computer. Mission control personnel can radio new instructions for storage or can bypass the computer to control the orbiter directly. Operating on these instructions, the lunar orbiter will turn itself to aim its two camera lenses downward during picture-taking orbits. Then, as it soars over the desired areas, it will take a series of pictures. One lens will cover an area of 25 square miles and record objects as small as a card table. The other will make overlapping photographs of 440 square mile sections. During its mission, the lunar orbiter will take 160 pairs of pictures while filming 12,000 square miles, an area as large as the combined area of Massachusetts and Connecticut. While photography is in progress, the camera will begin to automatically develop and store the exposed film. Following each series of exposures, the orbiter will again aim its solar panels at the sun. When picture transmission takes place, the stored images will be sent in the form of an electronic signal produced by a light scanning the stored negatives. At Goldstone, near an abandoned gold mine in California's Mojave Desert, this 85-foot diameter antenna is the communication link with the lunar orbiter. It's similar to two other antennas in Australia and Spain, surrounding hills protected from random radio signals. The antenna control team tracks the orbiter with signals the orbiter sends back to Earth. The team also directs the flow of signals from the antenna to the orbiter. This equipment generates signals to the spacecraft. The orbiter's computer responds to the signals and controls the orbiter accordingly. These men are the last human link between Earth and the spacecraft. Incoming photographic information from the orbiter is fed into this equipment, where electronic wizardry converts the electronic signal to a pinpoint of light of varying intensity. The tiny beam sweeps back and forth, exposing a moving strip of 35mm film. When processed, the resulting negative shows what the orbiter's camera saw. At the receiving station, technicians will process and study samples of the exposed negative to ensure that signals are coming back properly and that the orbiter's camera is correctly set. Most of the 18 miles of film will be sent to a reassembly facility where the strips will be developed and arranged into large negatives. Prints of these negatives will form the basis for lunar maps. Although direct communication with the lunar orbiter is via Goldstone, or Australia, or Spain, the mission is directed from the Spaceflight Operations Facility in Pasadena. Sitting side by side, NASA and Boeing engineers evaluate and act upon information received from the antennas. The information comes to the Pasadena Computer Center and is translated into a form understandable to engineers. They use it to determine the lunar orbiter's velocity, attitude, temperature, power situation, and some 50 other conditions. This automatic drawing machine charts the data. Other engineers keep track of the orbiter's location and direction. They plot course changes and calculate when and how the spacecraft should be maneuvered. This control room is the nerve center of the entire mission. The operations director and his assistant are in voice contact with key personnel at those installations throughout the world which gather and record flight information. Engineers here at Pasadena interpret the information, and the operations directors use the results to make final flight decisions. When its photographic mission has been completed in about a month, the lunar orbiter will continue to circle the moon, providing information about micrometeoroids and radiation in the moon's vicinity.
As you mentioned, we've known that the Van Allen radiation belts existed only since the late 1950s, when Dr. James Van Allen launched a series of rockets up into the Earth's upper atmosphere. The surprising discovery he made was that space is radioactive. Those early rockets carried Geiger counters capable of measuring radiation in space. As time went on, we realized they're quite extensive. The Van Allen radiation belts cover several Earth radii from Earth, and we've always thought, until now, that there were two of them. One close to Earth, about several hundred miles above the Earth's surface, and a second one further out, tens of thousands of miles above the Earth's surface. They pose a hazard to our spacecraft, and they pose a hazard to our astronauts, because radiation in space can cause cancer, prolonged exposure, and radiation in space can disrupt electronic circuits on spacecraft, can cause charging up and discharging on the spacecraft. They can simply ruin the spacecraft that we rely on.
Right, right. And yet these belts have not been fully explored, apparently, right?
That's right. A series of spacecraft have been there, but they haven't been fully instrumented. There's never been two identical spacecraft there at the same time capable of making the multi-point measurements that we need to have to understand what's going on. So we've had a fragmentary knowledge. We've had to put pieces together. We've had to make guesses. We've had to make assumptions. But now, for the first time, we've got two identical, fully equipped spacecraft going in and out through the radiation belt several times per day to give us the picture we really need to understand what's going on.
That's right. You know, there was another spacecraft called Sampex, which was orbiting in low Earth, and it was just about to re-enter the atmosphere, and we wanted to have an overlap so that we could enhance the science return from Van Allen probes. So we decided to turn on our instrument REPT, for relativistic electron-proton telescope, which measures high-energy electrons, a whole month ahead of what we had planned, just in order to overlap with the Sampex spacecraft. And to our surprise, we found this third radiation belt, and we were completely taken aback by it. We were not expecting it at all. And in the beginning, we thought, oh, maybe there is a mistake in our instrument. Maybe something is wrong with it. And as days went by, we became more and more certain that indeed it was nothing wrong with our instrument. Nature was giving us a spectacular show. So the third band, or the storage ring, or the radiation belt, lasted for about 4 weeks, I believe. It started off from a prior electron energization event, which we call when the electron fluxes increase. The solar event actually produces changes inside the magnetosphere, which make these belts get pumped up. So when these belts get pumped up, the number of particles in it get energized. They also increase in sheer number. So this is the radiation hazard that David was referring to just a while ago. And when this event happened, after this event, then there was another event which emptied the outer belt, but it obviously didn't empty the whole outer belt. There was an inner sliver of the outer belt left. However, then the energization occurred and the second belt came back on. And at this point, it should have at all become like one single entity. It did not. The sliver continued to last. So we had a 3 radiation belt structure lasting for more than a month.
We try to model the Earth's radiation belts. We use our most complex computer simulations to know what's going on, and no computer simulation, no model, has ever predicted 3 radiation belts. 2, yes. 3, no. And a third one that comes and goes, isn't there, is there. Things get swept up, things come back on these timescales in this way. Never happened before. So we have something fundamental here that we need to try to understand.
So basically, before I hit the play button, let me talk, what we're looking at. Obviously, there is a star background, but these white lines that we're looking at, this is a schematic representation of the magnetic field that actually controls the behavior of these high energy particles that the radiation belts are consist of. And you can see this stable inner belt, which will not maybe be as stable during this simulation or animation that I'm showing for reasons that I can go into. But more importantly, you are looking at the slot region and this second belt, which actually is not the full second belt, but the storage ring that you guys introduced earlier. And this animation starts, and I'm going to hit the play button right after one of these systems from the sun came and destroyed the outer portion of the outer belt and just left the storage ring sitting there.
Storage ring is, we should tell people, is lingo for the third belt, right?
That is correct. And the color in this animation basically represents the intensity of radiation in the belt. The brighter the color, the more red the colors are. It means that the more intense radiation levels are in this specific place in the belt.
Days after leaving Earth, the astronauts return, carrying with them the equipment recovered from Surveyor 3.
Investigators took a look at this camera and sampled it for microbial growth, and surprisingly got growth from one of 33 locations that they sampled.
They find something alive on a camera that's been on the surface of the moon for more than 2 years.
Not only did the investigators pick up sampling equipment hold it against their bare arms and put it back again. One investigator actually breathes on the camera area that they were going to sample.
But both current and former NASA scientists reject the contamination hypothesis. The presence of only one kind of organism makes contamination after Apollo 12's return seem unlikely.
They only found Streptococcus mitis. Now, if they had contaminated that camera while they were working, you cannot sneeze and produce only Streptococcus mitis. Someone who was assembling the camera may have sneezed or coughed and got Earth-human microorganisms into the camera lens area, and then it went to the moon. Now, why would they just find one microorganism on the moon? Well, the answer is very simple. Most of them died. But this little hardy beggar called Streptococcus mitis decided that it didn't want to die, and so it just sat there and stayed there on the surface of the moon for 2.5 years before the Apollo 12 astronauts came and got it.